Hubble's constant is the most important number in cosmology. It is the rate of expansion of space. It's the rate of expansion of our universe. When we look around us, all the galaxies, with the exception of a very few in the local group, are all moving away from us. They're all moving away from us, and the farther we look, the faster the speed at which they're moving away from us. So what we call h0, or the rate of expansion of the universe, or Hubble's constant, tells us how big the universe is, how old the universe is, and so on. Now, let's see if you understand what this means, this rate of expansion of the universe. Let's assume that this rate of expansion of the universe, h0, is 20.5 kilometers per second for each million light years. This is a fairly close number to reality, actually. So let's see what this means. It means that every million light years, so this is per million light years, we should observe the galaxies going 20.5 kilometers per second faster. So if we observe a galaxy at 1 million light years, it'll be going away at 20.5 kilometers per second. If you look at a galaxy that is 2 million light years away, it'll be going twice as fast, or 41 kilometers per second. If you look at a galaxy that is 3 million light years away, it'd be going 3 times 20.5, or 61.5 kilometers per second. So that's what rate of expansion of the universe means. To find the rate of expansion of the universe, we need two things. We need to know how fast these galaxies are moving away from us and how far away the galaxies are. Then we can find out what the rate of expansion of the universe is. This astronomer, Henrietta Leavitt, in 1908, she discovered the period luminosity relationship of Cepheid variables in the Large Magellanic Cloud. By looking at the Cepheid variables in Large Magellanic Cloud and looking at the period of variability, she was able to figure out that there is a relationship between the luminosity, how much energy is coming out of these stars, and how long it takes them to change their light. This is a graph that we come up with. This is the period of variability in days. So if a star, a Cepheid variable, changes in 6 days, its luminosity can be figured out here. If it takes 10 days, then luminosity can be figured out here. If it takes 30 days, then luminosity can be figured out here. It turns out that these Cepheid variables are red supergiant stars. And the longer they take to change their light, the more luminous they happen to be. And we can get the luminosity directly from the period of variability. What this allows us to do once we get the luminosity is to find out how far away they are, because we can measure distances to Cepheid variables that are close to us. We can compare the ones that are close to us to the ones that are farther away by using the inverse square law of light. So that's how we were able to find out the distances to faraway objects. This man, Edwin Hubble, took advantage of the variability luminosity relationship. What he did, he found some Cepheid variables in the Andromeda galaxy, and for the first time we found out that the Andromeda galaxy was outside of the Milky Way. This made the universe much bigger than it was before. This is the original plate where he found this one star here, and he had put down an N as in nova, a new star. And then he came back and changed it to VAR, means variable. So by looking at this one star for a period of time, Hubble was able to find the period of this variable star we call the Cepheid variable in the Andromeda galaxy. By knowing the period of this star, he was able to find the luminosity of this star. And then he was able to figure out how far away the star was. Initially, his numbers were a little off, but now we know it's about 2.2 million light years away, which is way outside of the realm of the Milky Way galaxy itself. Back in the early 20th century, the thought was that the entire universe was the Milky Way galaxy, that the spiral nebulae, is what they call the galaxies, were inside the Milky Way galaxy. Well, this discovery made the universe much, much, much bigger. It turns out that the rate of variability for what we call the V1 Cepheid variable in Andromeda galaxy was about 31.4 days, and that gave us the luminosity and then the distance. To find the speed at which the galaxies are moving away from us, something called redshift or recessional velocity, what we need is the Doppler shift of the light of the stars or the nucleus of the galaxies. So it's basically a simple Doppler shift. When we look, all the galaxies, with the exception of a few, are redshifting. That means their light appears to be moving away from the observer. The more redshift there is, the higher the velocity that the object is moving away from the observer. We look at the absorption lines in the spectra of the galaxies, and what we see is they either blue shift, which means these dark lines in the spectrum move towards the blue end of the spectrum, or they redshift, like here they're moving towards the red end of the spectrum. The more they shift towards the red end, the faster the object is moving away from us. So radial velocity is the object's velocity away or towards the observer. Recessional velocity is the radial velocity away from the observer. So as the universe expands, we say the galaxies are recessing from us. They're moving away from us. That's called recessional velocity. This recessional velocity is equal to change of wavelength divided by the actual wavelength times the speed of light. So when we look at the spectra of galaxies, we can see at rest, that means there's no motion at all. These are the spectral lines, so we can see some of these dark lines in the spectrum. If the galaxy is moving away from us, receding from us, then all the lines would have shifted towards the red end of the spectrum. What this means is that if an object appears to be bluish in color, it might turn out to be yellow. It might appear to be yellow to us. So the light is actually shifting its wavelength. Now, how much this line is moving, as an example here at rest, the dark line is over here, and it's shifted just a little bit here towards the red end of the spectrum, and this galaxy is shifted a little bit towards the blue end of the spectrum. So this galaxy is red shifting, this galaxy is blue shifting. That amount can be figured out by the actual shift. So the shift is measured in nanometers. And we need a specific line. Let's say this line here has a wavelength of 656 nanometers. Now, if we measure this line, we can see it's moved towards the red end of the spectrum by 65.6 nanometers. Then we can figure out how fast this galaxy is moving away from us. In this case, recessional velocity is going to be equal to 65.6, which is the amount of the shift, divided by the actual wavelength of that line, which is 656 nanometers, multiplied times the speed of light, which is 300,000 kilometers per second. Well, approximately, very close to. In this case, the recessional velocity of the galaxy is going to be 30,000 kilometers per second. That's how fast the galaxy is receding from us. Now, galaxies that are receding faster, like as an example, this is a spectrum of a galaxy moving at 61,000 kilometers per second. They appear to be farther and farther and farther. So this one is about 4 billion light years away. This one has got less shift. It's only shifted this much. is 2.5 billion light years away. This one here is shifted less. It's about 1 billion light years away. This one has shifted just a little bit. This one is 78 million light years away. Now Hubble and his friend Humason. Now Humason is a really good story because he was a mule driver for the observatory. He was carrying stuff up the mountain. Eventually Humason is going to become world famous astronomer. Together they worked on this problem. They measured the radial velocity or recessional velocity of some galaxies. Each one of these dots represents the distance in millions of light years and also recessional velocity of a galaxy. So this one here, you go down and you can see the distance is about 20 million light years and it's moving away at 5,000 kilometers per second. So he got a few galaxies and then he drew this line from 0 and 0, which is where we live, the Milky Way galaxy. He drew a line right through all these dots. This is called the best fit line. Now, the slope of this line gives us what we're looking for. The slope of this line gives us the Hubble constant. Remember, the slope of this line is rise over run. So rise can be right over here. There's the rise, and this is the run. So if you look at this line here, we say, okay, so this is about 10,000 kilometers per second. And we go down, that's about 60 million light years away. So something that is 60 million light years away would have a recessional velocity of 10,000 kilometers per second. So the farther the galaxy was, the faster it was moving away. His original data was off a little bit. He figured it out as 150 kilometers per second per each million light years. That's from a long time ago, 1931. Eventually, we figured out better and better numbers. Today, we think that the Hubble constant is about 20.5 kilometers per second per million light years. When we look at the galaxies, we can see the ones that are closer by, they appear to have less redshift. The faster they move away, the farther they are, and the more redshift they have. We can see these lines are shifting more and more towards the red end of the spectrum. Now, the distance to a galaxy can be measured by knowing the Hubble constant and the recessional velocity of a galaxy. So the way we do it, we look at the spectrum of a galaxy and measure the redshift. From the redshift, we can figure out how fast the galaxy is moving away. By dividing that recessional velocity by the Hubble constant, we can find the distance to a galaxy. Here's an example. How far away is a galaxy that is moving away at 3,000 kilometers per second if the Hubble constant is 20 kilometers per second per million light years? So we say distance is equal to recessional velocity divided by the Hubble constant. Distance is equal to 3,000 kilometers per second, that's the recessional velocity, divided by the Hubble constant, in this case 20 kilometers per second per each millions of light years. When we divide 3,000 by 20, we get 150. Kilometers per second cancels out with kilometers per second. Millions of light years gets multiplied to the top, and we get 150 million light years. That's the distance to the galaxy.